Hey, welcome back. So, have you ever looked at a light bulb or your phone charger and seen that little W on it? Ever wonder what that actually stands for? Well, you're about to find out. Today, we're going to demystify electrical power and figure out what watts are really all about.
Seriously, it's everywhere. On your microwave, your TV, pretty much every electronic device you own has that little number followed by a W. But what is it actually telling you? What in the world is a watt? Let's just break it down.
All right, so to really get a grip on power, we have to build on what we already know, right? If you remember, we said voltage is the push and current is the flow. Well, power is what happens next. It's the result of all that action. It's the actual work that gets done. Now, the key word here, the one you really got to remember, is rate. Power isn't just about how much energy is used, it's about how fast it's being used. You can think of it as, the intensity of the work being done, whether that's making light, creating heat, or spinning a motor.
So let's just quickly go back to our favorite analogies. Voltage, that's the push, the pressure in the system. And current, that's the flow of all that electricity. These two are the essential ingredients we need to cook up some power.
So, when you combine that electrical push with that electrical flow, bam, you get power. It's the direct measure of the work being done by the electricity in that circuit at any given moment.
And of course, this relationship is captured in a really simple but incredibly powerful formula. Power, which we represent with a P, equals voltage, V, times current, I. P equals V times I. This is the absolute foundation for everything we're about to explore. So, let's talk units. Power is measured in watts, voltage in volts, and current in amps. Now, 1 watt is defined as 1 joule of energy being used every single second. Just think of a joule as a tiny little packet of energy. So a watt is just telling you how many of those packets are being consumed every second.
Okay, theory is great and all, but let's see how this stuff actually works in the real world. We're going to plug some numbers into our new favorite formula and see it in action. Let's make it make sense.
So, imagine we have a pretty simple circuit. It's got a 12-volt push behind it and a 2-amp flow going through it. The big question is, how much work is actually being done here? How much power is this thing consuming? Well, the math is about as easy as it gets. 12 volts multiplied by 2 amps, that equals 24 watts. Simple as that. This means our little device is using 24 joules of energy every single second it's running. It's really that straightforward. And this is exactly what that wattage rating on your light bulb means. If it says 60 watts, it's literally burning through 60 joules of energy every second. So naturally, a higher wattage means more power. That usually translates to more output, like a brighter light, but it also means more heat and, for sure, more energy being used.
Okay, so P equals V times I is a fantastic start, but we can actually expand our toolkit. By combining that formula with our old friend Ohm's law, we can unlock 2 more incredibly useful ways to calculate power.
Now, watch how this works. It's actually kind of neat. We start with P equals V times I. And we know from Ohm's law that V equals I times R. So, what if we just substitute I times R in for V in our power formula? We get P equals I times R times I. You just simplify that and you get P equals I squared R. Pretty cool, right?
And we can play the same game again. We can rearrange Ohm's law another way, right? I equals V over R. So let's substitute that into our original power formula. That gives us P equals V times V over R. And when you simplify that, you get P equals V squared over R. And just like that, we have a complete set of power tools.
So here they are, all 3 power formulas together. You can think of this as your ultimate power cheat sheet. Each one is perfect for a different situation, depending on what information you have about your circuit. This kind of flexibility is an absolute game changer when you're analyzing circuits. Now I know, all this math might seem a little abstract. You might be thinking, okay, why do I need 3 formulas for this? Well, it has critical, real-world consequences. For engineers, calculating power isn't just an exercise. It's absolutely essential for designing things that are safe and reliable. You see, every single component in a circuit, like a tiny resistor, has a power limit, a maximum amount of power it can handle. Engineers have to calculate the power running through every little piece to make sure it can take the heat without, well, overheating, failing, or even worse, catching on fire. So let's look at a quick example. Imagine you have a resistor that's rated to safely handle 5 watts, but the circuit you've designed is actually pushing 8 watts of power through it. I mean, you can see the problem right away, can't you?
Yeah, the result is not good.
That resistor is being pushed way beyond its limits. It's going to get hot, it's going to burn out, and it could easily take other expensive components down with it. This, right here, is exactly why power calculations are so important.
Okay, now let's bring this all home and connect it to something we all have to deal with, our electricity bill. Because the whole concept of power is directly tied to how much you pay the utility company every single month.
If you've ever actually looked at your utility bill, you've probably seen this weird unit, kilowatt hour. It just looks like a jumble of letters, but it stands for kilowatt hour, and it's the standard way your energy consumption is measured.
So what is it? Well, it's actually pretty simple. A kilowatt is just 1,000 watts. So if you run a 1,000 watt appliance, like a small heater, for 1 full hour, you've used 1 kilowatt hour of energy. Your bill is really just adding up all the kilowatt hours you use all month long.
So, to wrap it all up in a neat little bow, voltage is the push, current is the flow, resistance is the opposition trying to slow it down, and power is the actual work that gets done because of all of it.
So now you have a really solid handle on the 4 core concepts of electricity. And that sets us up perfectly for our next big question. Now that we know what power is, how does it behave when we start splitting up circuits into series versus parallel? That's a fun one, and we'll tackle it in our next explainer. Thanks for diving in with me on this.